Pulmonary function. We're going to now start looking at the cardiovascular functions of the human body as it relates to exercise. So the first bit is to look at the pulmonary system. So that is dealing with the lungs and movement of oxygen, carbon dioxide, essentially gas exchange. Okay, so the pulmonary system has essentially two major functions. The first of which is one that's more widely discussed, and that is oxygenation of blood. So bringing in oxygen to then be used in our bioenergetic systems, other metabolic processes. Um, and then the removal of carbon dioxide, CO2, which helps with maintenance of pH. All right, so we're going to get over, we're going to look over these various roles throughout this lecture and help to sum all that up for you. All right, so just to start with the very basics, breathing. Breathing quite simply occurs by contracting and relaxing the diaphragm. Okay, so if we're talking about normal resting breathing, like you probably are doing right now, what happens is you have kind of they call it a negative pressure breathing system. Okay, so what happens is when you want to inhale, okay, or inspire air, what happens is the diaphragm kind of pulls down, okay, and when it does, the lungs are expanded. Okay, so the lung area increases, and if the volume inside of a container increases, and the number of gas particles or things inside that container stay constant, well then the pressure relative to the outside of that container, assuming they're in equality or if they were equal to begin with, well then it would go down, right? Because you have less things exerting pressure on the walls. So what happens is the thoracic cavity becomes low pressure system and air rushes in. So your diaphragm contracts, pulls down, lungs then fill up with air from the outside. Once the diaphragm relaxes, it goes back up. Okay, and the total volume here becomes less than it is here, and the opposite happens. Okay, so if you take the same amount of stuff or air inside of the lungs but decrease the size of the lungs, it has a high pressure. High pressure overcomes that of outside air, and it moves out of your mouth. Okay, it's quite simple. It's just relaxing and contracting the diaphragm, causing air to either flood in or be pushed out through positive and negative pressures. And when the air comes in, you see we have the trachea, so the air comes in through your mouth, it goes down the trachea, it then bifurcates out to the bronchi, okay, and eventually it's going to go down to much smaller little vessels and make their way over to the site of gas exchange, which is the alveoli. Okay, so you have these alveolar sacs, and that's where we actually exchange oxygen and carbon dioxide. Okay, a little bit of the anatomy of these guys. They're very very thin membraned, which allows for oxygen to come in more easily, CO2 to leave more easily, and it's highly vascular. So you have a lot of little capillary beds that are kind of surrounding these alveolar sacs, and so blood gets pumped from the right ventricle up to the lungs. That blood is fairly deoxygenated. Oxygen diffuses across the membrane of the alveolar sac into that capillary bed where it meets with hemoglobin, Um, and carbon dioxide exchanges a bit like the opposite. Okay, so this is our site of gas exchange. All right, so as I was saying a second ago, hemoglobin, or red blood cells, are the thing that takes up oxygen, carries it in the blood. Okay, um, the heme portion of this is an iron within that, and that's what actually binds with the oxygen. All right, so there's various aspects which influence the transport of oxygen, which we'll deal with a bit later. But anyway, you can have some difference in the affinity of hemoglobin for oxygen, depending on things like acidity, temperature, um, pressures, that sort of deal. Okay, and also training. Uh, those who are more trained have a better capacity for oxygen transport. All right, so let's talk about our first, um, say, bit of nomenclature coming out of all this. All right, minute ventilation. Okay, so minute ventilation is is the amount of air that we move each given minute. Okay, so minute ventilation, because ventilation strictly speaks to the movement of air. It doesn't really speak to what's happening as far as gas exchange. So volume of air expired by the lungs each minute is the definition of minute ventilation. Right. So quite simply, if we were to look at that, we could take tidal volume, if we were to break it down a little bit. So if tidal volume is the amount of air that's actually leaving the lungs with each breath. Okay, so every time you breathe in and then breathe out, there's a certain amount of air that's going to stay in your lungs so they don't completely um, deflate, and a certain amount is going to leave. Okay, the amount that leaves is the tidal volume. All right, and then the other portion is breathing frequency. Okay, that makes sense. So you have a volume here, and then you have a frequency. That's going to give you liters per minute, right? So volume and a certain amount of time, right? Time, frequency, same kind of deal, right? So VE, as we go forward and we talk about VE, we're talking about minute ventilation. This is a simple way to talk about, how much you're breathing at any given moment, which has to do with a few different things, which we're going to talk about. All right. One of which is the basic respiratory control center. Okay, pons and medulla oblongata are the center of this. All right, there's three major neuron groups: the medullary rhythmicity center, the pneumotaxic, and the apnostic. Okay, and they each have their own distinct jobs, which we'll go over briefly. As this isn't really a neuroanatomy class, I just kind of briefly touch on these things. But the medullary rhythmicity area controls basically your 9 to 5 general relaxed breathing. Okay, so under this system, most people will have an inspiration, or they'll breathe air in for about 2 seconds, and they'll breathe that air out for about 3 seconds. All right. So what happens is you have these autorhythmic cells, or autorhythmic cells. They activate for about 2 seconds, and then afterwards they become inactive. So that's when you're having that inspiration that's causing the diaphragm to drop out, to contract, and then afterwards the relaxation in these areas cause the diaphragm to do the same, relax. Okay. So when you're at rest, only the inspiratory system or area is actually active. Okay. If you go into more difficult breathing, more labored breathing, you have the activation of what's called the expiratory area. Okay. So within the expiratory area, you actually get an increase in what we call them assisting muscles. Okay, both in the exhalation and inhalation side. Okay, and then roughly we can just characterize this as having additional muscles having addition muscles around the thoracic cavity and or up in the neck. Um, Basically, the muscles surrounding the pulmonary system get activated, which causes more forceful breathing, both in and out. So you have more forceful inspiration and more forceful expiration. Okay, so then you have the pneumotaxic area, and that is dealing with inhibitory impulses to the inspiratory area. So that is basically telling you to stop breathing. Okay, and those neurons essentially activate to keep you. If you were to think about it, if you take a really big deep breath, um, this is the area of the brain stem there that's going to activate to tell you to stop breathing, so you don't expand too much. All right, and on the other side of that, you have the apnostic area, and that stimulates longer periods of breathing. So you kind of have them doing opposite things there. One telling you to stop breathing, the other one is telling you to breathe. All right. So other factors regulating respiration or minute ventilation. Okay. The primary thing that we're going to talk about will be metabolic byproducts. Okay. Carbon dioxide and hydrogen. Okay. Hydrogen ions and CO2 lead to changes in pH of the blood. And when you have a change in pH, then there's lots of problems downstream. We'll talk about that a bit more in a second, but major factors: one, metabolic byproducts, and two, of course, is your ability to actually just change the way you breathe, right? Probably some of you, I know myself, when I start talking about the lungs, I start talking about pulmonary and minute ventilation and the inspiration systems and the expiration, I actually start being much more cognizant of the way I'm breathing, right? And I start having more control over it, right? But you could certainly decide to hold your breath or breathe more rapidly, hyperventilate. So that's something else. You can just, it's one of the systems that's somewhat unique with breathing is if you don't think about it, it'll go by itself. Much like the heart rate. Your heart keeps beating. You don't have to tell it to beat each time consciously. Your central nervous system just takes care of it. Your lungs are the same way. If you don't think about it, you'll just keep breathing. But if you want to, you can certainly hold your breath or change your breathing pattern. Right? In fact, it's quite necessary for something like swimming. Now the limitations of this are back with the metabolic byproducts. If you have too much CO2 or hydrogen, that will supersede your decision to voluntarily breathe in most people. Okay, say most people because there's kind of that classic example of a misbehaving kid who says, "Oh, I'm gonna hold my breath until I die," to their parent, and some parents will go, "Oh no, Timmy." But good news is, for those of you who will go on to become parents, if your kid ever does this, you can call their bluff, and you're going to find out something that's good to know about your kid, how much willpower they have. So one thing, they'll either hold their breath for a while and then they'll let it go and breathe really fast afterwards, or they'll go through with it. They'll hold their breath so long that they pass out. In either case, you'll get your way because you'll have stood your ground. If they do actually pass out, though, good news is at that point, once their central nervous system shuts down, at least from the waking portion, the consciousness, you'll automatically start breathing normally again. So little Timmy will learn that if they mess with the bull, they get the horns, and then you're not gonna bow to their whims, or anyway, you win. So don't give in to terrorism. All right, so let's look a little bit of physics. Dalton's law. Okay, so Dalton's law just essentially states that the the partial pressures of any number of gases, individual gases, exert an overall pressure, okay, um, in a system. So atmospheric pressure is 760 millimeters of mercury at sea level, and that is directly proportional to our pressure of oxygen, pressure of CO2, pressure of nitrogen, and pressure of water vapor. Okay, so that's what our air pressure kind of looks like, and we bring this up because I'm going to talk a little bit about air and how it relates to what's coming in and out of the lungs. Just want to bring this up so some things are kind of made clear. Now, something that should be noted though is if you ever tried to exercise in a humid environment, what you'll find is, at least I find, it's harder to breathe. I find it more difficult to do aerobic activity if it's very humid. Now, part of that is certainly that it's typically warmer outside when it's humid, so sure, temperature comes into play. But there's also the idea that if this is true, if we can accept that Dalton's law is true and that each one of these individual pressures is exerting their own force, well then, while atmospheric pressure might be the same, if we have an increase in either any one of these factors, you have a decrease in the other ones. Okay, so say that if it's very humid and we have more water in the air, right? And we have more water vapor. So if I'm breathing that water vapor in, then as a consequence, the pressure of oxygen, nitrogen, and CO2 are going to be lower. Okay, so that might mean that I'm going to have a reduced ability to take up oxygen, which could hurt my performance. Okay, and the same is true for any one of these gases. Okay, so the composition of air. Okay, the air you're breathing right now is probably something about 21% oxygen, little under 80% nitrogen, and a very small percentage of CO2. Okay, because there's always carbon dioxide in the air, just very, very little bits of it. Okay, much less than 1%. Now, alveolar air. So this is the air inside of your lungs. Okay, alveolar air, if we look at this, has about about 2/3 that of normal air, oxygen level. Okay, so about 7% is being taken out. Right? And nitrogen is exactly the same up here and down here. CO2 significantly higher, right? So it's about, pretty much about all this, right? It's about 5.2% higher. Now, remember back to when we're looking at the metabolics and we're looking at bioenergetics. Okay, we're using oxygen in the electron transport system, so it makes sense that we're going to extract air, and then we're producing carbon dioxide in the Krebs cycle. Okay, so metabolically, that's where we're getting these things. And if we look at expired air, so we have air from the outside, air that's inside of your lungs, and an air that's being measured at what you're breathing out. The reason that these numbers aren't, the reason that these things are not equivalent here and here is simply that within your trachea, there's a certain amount of air, we call it dead space, okay, where no gas exchange is happening, and that air is the same as this, like your outside air, plus this air. So you get kind of a combination of the two. There's much more air in the alveoli, so you're not getting as much. Maybe it's something like 80% of this, 20% of this, probably less than that even, but something like that, where those things are mixing together. So the air you're actually going to observe, if you were to hook someone up to a gas analyzer, is a bit like this. You'll see about 4.5% CO2, and then about 16% oxygen. All right, so let's talk about regulation a little bit. Okay, getting into the important stuff here. All right, so as I mentioned earlier, we regulate our breathing to a certain extent based on metabolic byproducts, namely hydrogen ions and the pressure of CO2 in the blood. Okay, now those things are picked up by chemoreceptors. Okay, so chemo, if you want to think about this, think like chem, like chemistry. Okay, think chemical receptors. Okay, so we have central and we have peripheral. Central are having to do with the central nervous system, so it's in the medulla. Okay, and anyway, when there are chemicals such as hydrogen or carbon dioxide, when those levels become elevated, then you have a change in your breathing pattern. Okay, the stimulation is to cause more breathing. Okay, now terminology, if you ever see this term here, hypercapnia, hyper meaning higher, capnia referring to pressure of CO2. Anyway, hypercapnia speaks to an increase in CO2 in the blood. All right, so as I said, we have peripheral as well. So peripheral dealing with areas outside or away from the central nervous system. Okay, same thing. They respond to hydrogen, CO2, in this case oxygen as well, and they're located in the aortic body. Okay, in the aorta, for those who aren't, drawing a blank here, the aorta is of course the main artery coming off of the heart. Okay, and that's the big artery that everything splits off of. That go. We'll talk about this much more later. But anyway, in the walls of the aorta, you have receptors for these metabolites, and then also in the carotid body, carotid artery, carotid, of course, goes to the brain. That's another receptor site where these chemicals are sensed. All right. Another thing more things that influence breathing rate are proprioception or proprioceptors. So proprioception, easiest way to explain it is kind of how you perceive or how your body perceives motion innately. So if you were to think about it, if you closed your eyes and maybe just started to move your hands around, as you're moving your arms around, you're moving your hands, your fingers even, in your mind you probably have a mental image or an idea of where your arms are in space. That is what we would call your proprioception, your kinesthetic awareness, all kind of the same thing. Okay. Other than that, you have anxiety state. So if someone is worked up, so to speak, if they're having an anxiety attack, something like that, their breathing rate will be increased. If you have a higher temperature, you breathe faster. And also drops in blood pressure. If your blood pressure starts to drop, breathing rate will increase. All right, so you have an inflation reflex, which is if you take a big deep breath, you will have an innate urge to exhale. That's just a response you have within your system. Other things that influence breathing. In this case, we have reduction of breathing, apnea, or just stopping of breathing, cessation of breathing. If you have a sudden plunge into cold water, that'll cause people to hold their breath momentarily. If you have pain, it will also cause people to hold their breath for a second. Or also irritation of the airway. So if the airway itself is irritated or say inflamed, it can slow down breathing rate. Okay, so ventilatory responses to exercise. So we're going to put this together a little bit more, but essentially, the harder you work, the faster you breathe. Probably didn't need to tell you that, guys, that. You've probably all experienced that. But we're going to move forward with this. We're going to talk a bit more about why this happens, okay? So for sure, the harder you work, relative to your VO2 max, the faster you're going to breathe, the more you're going to breathe. And that relates to a number of things, but we're going to talk about that in a second. Alright, so ventilatory breakpoint. Ventilatory breakpoint describes to a certain extent what we just saw in the last slide, which was the faster you work or the harder you work, the more you breathe. Okay, so the ventilatory breakpoint is the point where your ventilation increases disproportionately to oxygen consumption. All right, and this will be made clear in a second. I got a graph, but essentially, as you're starting to exercise, if you're sitting right now, you've got a very low need for oxygen, so you're going to be breathing just about as much as you need oxygen. Okay, so at low work, we could see, let's say, oxygen use here will be in blue, and then ventilation, we'll say, is in pink here. Okay, so at rest, what happens is you breathe just about as much as you have to in order to get oxygen in. All right, but there's a kind of an interesting thing that happens right around lactate threshold, or about 60-ish% of VO2 max, depending on training status, of course. Okay, when you start crossing lactate threshold, and you start deriving most of your energy from glycolysis, what happens is you start producing a lot of hydrogen. Okay, you start becoming more acidic, and that indirectly causes an increase in CO2 levels. All right. Now, CO2, carbon dioxide, is the single greatest thing which influences your breathing, other than, say you just deciding to hold your breath. So the production of CO2 is the thing that's actually causing you to breathe for the most part. Okay? If you weren't producing CO2, if those levels weren't registered, you'd breathe a lot slower. So, let's just take a look at this a little bit. So, but to continue here, if I were to continue this graph, and we say we had intensity on the x-axis here, if I started working at a certain point, my oxygen consumption would remain stagnant. Okay, it would increase the harder I work, but it wouldn't have an exponential growth. It's still, you see, it's very linear. Okay, but once I hit lactate threshold, we'll say this is LT right here. What happens is that you start seeing this. You start breathing more. You start breathing a lot. You start breathing very rapidly. Although your oxygen needs stay about the same. Okay, reason being is you're starting to produce a lot of CO2, massive amounts of CO2, and your body, as I said a second ago, your brain is stimulated. Okay, there's lots of CO2 being produced. I must be working really hard. I need to get rid of it, because if not, I might become acidic. Okay, and if you become acidic, there's some problems with that. Namely, every enzyme in your body, the ones that govern muscle contractions, the ones that govern all the bioenergetic systems, every single enzyme in your body has an optimal temperature range. It also has an optimal pH range. It has an optimal range for that acidity. So if you become more acidic, if your pH drops, what happens is your enzymes, which are helping to catalyze reactions, they'll slow down. And if they slow down enough, you can actually die from that. Which is why it's a problem if your blood becomes too acidic. So that's why, your body tries to keep it very well regulated. Enter the pH buffering system, bicarbonate buffering. Okay, so if we look at this, this looks a little bit convoluted. I'm going to break it down a little bit, hopefully make it a bit more understandable. Okay, so CO2, water. Okay, so this is water, of course. We have this all over our body. Okay, so assume we just kind of have water all over the place. This is why, so I'm gonna, as I go through this, once again, I'm trying to explain to you why you breathe faster when you start to go past your lactate threshold, when you start working at a very fast rate. Okay? And here's why. Okay? Normally, if you're just say sitting here, okay, as I'm sitting here as well, metabolically I'm producing CO2. Okay, the CO2 is going to come out of my Krebs cycle. It's going to bind with water, and then it's going to form carbonic acid. Carbonic acid is kind of the carrier, if you will, of those excess carbons and carbon dioxide in the blood. All right, so it's going to go to carbonic acid. These two things just will associate, CO2 and water. Boom, I have carbonic acid. That's going to be carried along in the blood. Once it goes to the lungs, what this reaction first did this, then it'll reverse, okay? Then it'll go to CO2 and water. The CO2 gets breathed off, okay? I breathe that away. And the water, some of it will be breathed out, some of it will just be, most of it will just be regulated or recycled. Okay, so that's under resting conditions or low intensity. This is all we're dealing with right here. CO2 goes with water, creates carbonic acid. Carbonic acid goes to the lungs. We breathe off the CO2 and the water remains. Lovely. Okay, I produce more CO2. I grab up more water, create carbonic acid, breathe off the CO2, and we keep doing this dance. Okay, so that's where you're breathing off your CO2, no problem. But when you start to produce a lot of excess hydrogens through production of acids, or even just doing a lot of muscle contraction, because if you remember back, ATP hydrolysis releases hydrogen. So the more you're contracting your muscles, the more you're producing hydrogen, and that's going out into the blood. Okay. What happens is hydrogen, excess hydrogens are pretty much all pHs. So if we're talking about like pH balance, if something's acidic or alkali, whatever, all we're talking about is the concentration of hydrogen ions in that solution. So the more hydrogen, the more acidic we get. All right. So what happens here is if I'm producing a lot of hydrogen, it means I'm working at vigorous or high intensity. Okay, so I produce these hydrogens, and if I don't do anything with them, they're going to affect the pH of my blood. Okay, so your body will attempt to buffer that hydrogen production, and what it's going to do is it's going to take this substance called bicarbonate. By the way, if you guys are bakers, baking soda is sodium bicarbonate. It's basically the same compound with a sodium attached to it. Okay, and bicarbonate is located in most of your cells of your body. It's kind of all over the place. All right, and what it does is this bicarbonate is going to bind with hydrogen, and they're going to form carbonic acid. Okay, so what happens in this instance is if I'm producing a lot of hydrogen, a lot of acidity, acidity gets buffered by bicarbonate. It's going to go to carbonic acid. Carbonic acid is going to go to the lungs. It's going to breathe off the CO2. Water's going to stay. And that's how we're taking hydrogens and creating CO2 out of it, essentially. All right. So that's why you're getting more carbon dioxide the harder you work. Because certainly, if we're shifting over to glycolysis, glycolysis does not actually produce CO2, right? So you might be scratching your head a little bit if you were to look at that equation, because there's no CO2 produced in glycolysis, but we do get a decent amount of hydrogens coming off of that equation. Okay, and lactic acid also another hydrogen donor. So you see there, that's where we're getting acidity. With increased acidity, when you get acidosis of the body, you have to buffer it, or you have serious systemic problems. So we do that with bicarbonate, and then that's going to shuttle essentially the carbon off of the bicarbonate gets breathed off, and that's going to help to maintain our pH in our blood. And this is what this looks like. Okay, so we have oxygen uptake, we have breathing right here. It says a minute ventilation, and at a certain point you hit break point. Okay, that's going to be lactate threshold. Hit that lactate threshold, and then you see this kind of exponential increase in breathing rate or ventilation. And you guys can test this if you want. Quite simply, um, if if you start if you start off at a slow pace, say walking, jogging, something like that, you're not going to have any difficulty breathing or talking to somebody. There's something they call the talk test. The talk test is um, when you're jogging or running or something. If you want to work at a specific intensity that's below lactate threshold, they say that if you can't hold a conversation with somebody, that is, you can't say a full sentence without having to take a breath to breathe, then you're probably working too hard. You're probably past lactate threshold because you're breathing so much. If you're if you're able to hold that conversation and to talk normally with the person next to you, it means that your breathing rate isn't that fast and that you're probably below lactate threshold. So that's the talk test. And if we look at this, if we look at this control of pH, let's get rid of this. What you can see is pH will drop whenever you become more acidic, right? It's simple. You have increased concentration of hydrogen, and that increased concentration of hydrogen drops your pH directly. You become acidic. Okay. You can also become alkali. That is, if you have too little hydrogen ion. Okay, loss of acidity, and this can happen actually if someone hyperventilates. Okay, and it all has to do with your body sensing carbon dioxide. Okay, if somebody starts to hyperventilate, they're breathing really fast, so they're breathing out CO2 at a very fast rate. Okay. And that CO2 that's breathing out, once it's leaving the body, well, your body as a consequence is going to sense that there's less CO2, so you're not going to breathe as much. Okay. Um, uh, an example of why you might do this is if you've ever done, say, skin diving, where you grab a snorkel and some fins and just, I don't know, go up to maybe 20 feet down, grab some shells or something. What people do before they dive down, and sometimes in swimming, I think as well, you can see them hyperventilating. They'll breathe really fast, and you'll do this naturally. Like, I don't have to, like, no one has to tell you to do this. You don't have to go through this lecture to figure out how to breathe. Um, if even if I tell you, okay, you're about to go run really fast, you'll start breathing really fast. You'll start breathing at an elevated rate because your body knows that you're about to start producing a lot of hydrogen. You're going to start becoming a little bit acidic because our ability to get rid of CO2 is not going to be as great in the very near future. So, in general, people will just start breathing faster as a precautionary or a way of getting themselves ready for, in the case of diving, going down and not being able to breathe. In the case of, say, doing a sprint or lifting a heavy weight, it's that you might need to be holding your breath for a portion of that. And if you hold your breath, you of course can't be ventilating. Alright, so here's kind of a more expanded graphic that shows you the different things which can lead to increased hydrogen in the body. We see carbonic acid. We talked about that with the bicarbonate buffering. Lactic acid, of course, can donate hydrogens off. You also produce small amounts of sulfuric acid, phosphoric acid, and sometimes you'll produce these things called ketone bodies, which you produce a lot of if you're ever doing an Atkins diet or something like that. It's a ketogenic diet. All those things drop pH. So the buffering system works to convert that extra hydrogen essentially into carbon dioxide so you can breathe it off, and anyway, that's why you breathe faster. Alright, so let's talk about the respiratory system or your pulmonary system as a limitation to performance. Okay. First off, let's say this: there are very few people in the world who are actually limited by their pulmonary system. For this reason, not many people do pulmonary research because it's just simply not a limiting factor. Okay. So if we look at this in respiratory muscles, respiratory muscles, or rather the muscles dealing with your ability to ventilate, accumulate for they account for 15-ish% of the oxygen being consumed during heavy exercise. Okay, it can be more in some cases, but about 15%. All right. In extremely long-term activities, you could actually see fatigue in these muscles, which would hurt your performance. But in general, your pulmonary system, your lungs, have so much surface area, something around the size of a half a tennis court of surface area, that unless you have a pretty nasty disorder, that's not going to be the thing that stops you from exercising. Okay. You can have all kind of obstruction cases. You can have something like pneumonia, where you just have gunk and phlegm and mucus in your lungs, which then cause there to be a more obstruction of air or gas exchange. But other than that, if you're healthy, in general, you don't train to increase your pulmonary capacity. They'll increase while you're working on your cardiovascular training, but not directly.